Welcome to the third and final part of Unit 8. In this part, we are going to work some examples involving the force of friction. Here is the table again for the coefficients of friction because we will need them for one of the examples. In the first example, however, it is a strictly symbolic question. So we have a block on an incline and we want to show the form of the acceleration when the friction is zero or when the friction is kinetic. So we have a block sitting on an incline and we're told it's accelerating down the incline, so the acceleration is going to be this way in both cases. As with the example we did in the last unit with the block on the incline, we are going to take and cant the coordinate system so that y points perpendicular to the incline and x points down the incline. The angle the incline makes with the horizontal is theta, and as we saw last time, that makes this angle theta as well. If I look at the free body diagram for this block, I have the normal from the, I'm going to call it a ramp so that I have an R instead of an I here, the ramp on the block. I have the force of friction from the ramp on the block, and the normal force points along our y-axis, the friction points along the negative x-axis. And then the last force I have is the block's weight, which points along neither axis. But because I know that this angle theta is there, I can make this angle theta here. And now I'm going to define a triangle where the, whoop, that was supposed to change color. Let's try one more time. One leg of the triangle follows the y-axis, the other leg is parallel to the x-axis, and the weight is the third side. So now I have a triangle that looks something like this, where this is the angle theta, this is the weight, this is the y component of the weight, and this is the x component of the weight. I can find the y component in terms of the weight multiplied by a cosine of the angle, and I can find the x component by the weight multiplied by the sine of the angle. Okay. In both cases for this example, there is no acceleration vertically along the y-axis, if you will. So I'm going to begin there. So net force in the y direction will be MAY, which will equal 0 newtons. I have two forces in the y direction. The first is I have the normal from the ramp on the block. The other piece I have is the y component of the weight. That has to equal 0. Which tells me the normal from the ramp on the block has to equal WEBY, which is WEB cosine of theta, or in other words, mg times the cosine of theta. The next thing I'm going to do is I'm going to look at the first question where the friction is 0. So friction from the ramp on the block equals 0 newtons. In that case, horizontally, if you look, this force isn't there. So the only force horizontally I have is the x component of the weight. So when I write Newton's second law, F net x equals max, the only piece here I have is WEBX, which equals max. Or in other words, mg G sine theta equals max. The masses cancel, and the acceleration when I have no friction equals G sine theta. For the second part, I do have a frictional force. I know that that frictional force is going to equal the coefficient of friction multiplied by the normal of the ramp on the block, or in other words, mu k times mg cosine theta, where I've taken this value up here and plugged it in down there. I can now apply Newton's second law. I'm going to take all the forces in the direction of the acceleration, which in this case is the x component of the weight, subtract off all the forces in the other direction, which in this case is the frictional force. That has to equal mass times acceleration. The x component of the weight will be mg sine theta. Friction will be mu k mg cosine of theta. I notice that I have a mass in every term, so I can cancel it. I also have the acceleration due to gravity in both terms on the left-hand side, so I can factor it out. So now I have g times the sine of theta minus the coefficient of kinetic friction times the cosine of theta equals the acceleration. And if you look back one slide, that is exactly the formula that we got in the problem statement. Moving on to the second example for this section, we are going to be pushing a block along an incline. Oh, not along an incline. I'm sorry, I said that wrong. At an angle. So in this case, we have a block of ice on a frozen pond. So the coefficients of friction we want, if we flip back, are ice on ice, which for static is 0.1 and for kinetic is 0.03. So let's make a note of those. So coefficient of static friction is 0.1, coefficient of kinetic friction is 0.03. Okay. The contestant in this case is pushing on the block at an angle, and we're told it's a 25-degree angle. Okay, so that tells me this angle right here is 25 degrees. Using a standard XY coordinate system, I don't tilt my axes here because my acceleration will be along the surface of the ice, and it works a lot better if I keep my coordinate system so that one of my axes lies in the same direction as the acceleration. Drawing the free body diagram of the ice block, I have a normal force from the ice on, let's not do ice. I really don't like eyes because they can look like ones too easily. So we're going to call it the pond on the block. We have the block's weight. We have friction that is going to point this way because the person's trying to get it to move in the other direction. And then we have the normal from the contestant on the block. And again, that one's at a 25-degree angle. So the first thing I need to do is resolve that into components. So I'm going to take and define a triangle, one side parallel to the x-axis, one side parallel to the y-axis, and the third side along my force. So redrawing that, I have NCB, NCBX, NCB y and my 25-degree angle. So NCBX will equal NCB cosine of 25. And NCBY will equal NCB sine of 25. Okay. Again, this block isn't going to accelerate vertically. There's no acceleration that's going to happen in the y direction. So for both parts of the problem, the net force in the y direction will equal 0 newtons. I have three forces that act vertically. I have the normal from the pond on the block pointing upward. I have the block's weight pointing downward, and I also have a piece of the force from the contestant on the block pointing downward. That would be the y component, and that has to equal 0 newtons. The piece I need from this equation is the normal force from the pond on the block, because I have to plug that into the force of friction. So solving for that, normal from the pond on the block will equal the weight plus the y component of the force from the contestant. So that is mg plus NCB sine of 25. The mass we were told is 45 kilograms, so I can plug that in. 9.8 meters per second squared. Sine of 25 is 0.42. So multiplying that together results in 45 times 9.8. Sorry, I have to open my calculator here. 45 times 9.8 is 441 newtons plus 0.42 NCB. And that's as far as I can take that right now, because I don't know what the force from the contestant on the block is. Okay, in the first part, it's the minimum force he must exert to get the block moving. What that is asking for is how much force do you need to apply to overcome the maximum value of the force of static friction. So looking in the x direction, we have F net in the x direction is going to equal 0 in this case, because we want to know the force we need to apply to overcome static friction. There are two forces in the x direction. We have the other component of the force from the contestant, and we have the force of friction. NCBX is going to be NCB cosine of 25 degrees. Force of friction will be mu static times NCB in this case. At maximum, that's what that force can take on. So now I have NCB times the cosine of 25. The cosine of 25 is 0.91 times NCB. The coefficient of static friction we found from the table and wrote on the previous slide was 0.1. And we need to multiply that by our I wrote my subscript wrong here. This should be pond on block. We need to multiply that by the normal force from the pond on the block, which is 441 newtons plus 0.42 NCB. And yes, that is written correctly this time. Okay, so multiplying that out, I have 0.91 times NCB equals 0.1. I don't want an equal sign. Sorry, I want a minus sign. 0.1 times 441 is 44.1 newtons. Distributing the minus sign in, I get 0.1 times 0.42. And 0.1 times 0.42 is 0.042 times NCB, and all of that has to equal 0 still. I can collect like terms, so taking 0.91 and subtracting off 0.042 gives me 0.868 times the normal force from the contestant on the block. And moving the 441 newtons to the other side, 44.1 newtons. And now I can divide and find that the contestant is pushing with a force of 50.8 newtons. And that is part A. Let's go back now and look. Part B is asking, what force is necessary, what's the acceleration if that force is maintained? So we're going to keep pushing with the force that we just found, the 50.8 newtons. Okay. So now with that, I know for part B that I'm going to keep pushing with a force of 50.8 newtons. I can now find the value of the force of friction between the pond and the block using the formula that I found in part A, which is that using this result and the force of friction from the pond on the block will be the coefficient times the normal from the pond on the block. So in that case, since it's now going to be moving, I need to move over to kinetic friction. So that is going to be 0.03 multiplied by 441 newtons plus 0.42 NCB. Plugging the 50.8 into that as well and multiplying this all out. So I'm going to make a little arrow here. Do my best to actually point at what I want. This works out to be 13.9 newtons. I can now go to the x direction. That equals mass times acceleration. In the x direction, I have two forces. I have the normal from the contestant on the block in the x direction, and the force of friction from the pond on the block, which points in the opposite direction. The acceleration will be in the direction of the contestant as the problem is worded. That equals max. The normal from the contestant on the block will be NCB times the cosine of 25. The force of friction we just found was 13.9 newtons. The mass is 45 kilograms. I can take 50.8, plug it in for NCB, need to multiply by the cosine of 25, which is 0.91. And that has to equal the mass times the acceleration still. Multiplying and subtracting results in this side equaling 32.3 newtons. So now I can say the acceleration is going to be 32.3 newtons divided by 45 kilograms, which equals 0.72 meters per second squared. This concludes the second example of this part of Unit 8. It also concludes Unit 8. In the next unit, we are going to be looking at circular motion and gravitation.